Okay, so here we've been given a curve. We have this quadratic curve. Okay, so it's going to look something like this. Okay, and we want from 0 to 3. Okay, we know that that's the vertex is at 3, so we're going to say, let's say that's 3 there, and we want 3 intervals, and we want the trapezoids for these 3 intervals. Okay, and we can see that that trapezoids kind of are overestimating just a little bit. Okay, so then we want to calculate the displacement. We want to calculate these areas. So I'm just going to do a table of values here. So this is, let's say that's x, and this is y, and this is our, let's just do another one for area. So x is 0, y is 3, okay, x is 1, 2, y is going to be, when x is 1, I get 3.5. When x is 2, 2 squared, I'm getting 5. Okay, and then when we want to do these interval widths, so I'm going to have 3 here. I need 3. So 3 squared times 0.5 is, that's going to be 7.5. Okay, so then my areas that I'm going to calculate, I'm going to calculate 3 areas, and I'm just going to take out that so I can put my areas in here. This is my area, and I'm just using the grid to keep track of this. So this area here is going to be 3.5 plus 3 divided by 2 times the width of 1. So I'm getting 3.25 is my area. Between these two trapezoids, I'm getting, I'm just going to write it in, 3.25 for that one. This is going to be 8.5 divided by 2, which is 4.25. So it's going to be 4.25 is this area. Okay, here's going to be 12.5 divided by 2, so it's going to be 6.25 is my area here. Okay, so the sum of those areas, I'm getting 10.5, 13.75 units squared. Okay, so I can organize my trapezoids here. I got my table of values, and make sure that you can organize your area a little bit better. So again, I'm calculating the displacement. If this would happen to be, oh, this is a velocity function, so the area is going to equal my displacement. So the net displacement is going to be equal to 13.75. Let's assume it's meters per second. So let's say 13.75 meters is my net displacement of this velocity function. So in general, we can, now there is a formula, and you can probably look it up in the area under curve. This formula only works if the intervals are the same width. Okay, so be very careful with this formula. We can't just apply this formula, random or just for any trapezoids. This only works when the interval width is the same, because if the interval width is the same, so I have delta x the same, I can, for each trapezoid, I can factor that out, and then what ends up happening is, because the average height is going to use half of y1 here and half of y1 here, we get, y1 2 times divide by 2, we get actually y1. We can actually group together some of our terms here. This makes it a little bit more efficient. This is not that important because this only works in a special case when the interval widths are the same. I've given you a link here, so just practice doing these with on Desmos. There's some technology there that you can use, and use that link, and you can use Riemann sums and trapezoids to approximate areas. So again, in general, I've kind of reiterated this many times, but in general, what would make the Riemann sums and trapezoids fit better on the curves? That would be smaller interval widths. Okay, or delta x. And we want the delta x to go to, we want narrower and narrower, and we want to go to 0, but we can't make it 0. But we can see what happens when we take the limit as x goes to 0. And as x goes to 0, we start using different notation. We start using this dx. Okay, so that would be the difference when you see delta x versus dx. They actually mean the same thing, but this implies really thin. Now this is what we would consider measurably thin. And if we want to sum up the height times the width and all those rectangles to get the sum with that area, if we let the limit of delta x go to 0, we're now using calculus. Okay? And we start changing our notation. So this sigma here means sum. This little thing here is called an integral. And it's actually a kind of a nice stylized letter S because it also means sum. These actually mean the same thing. And what this means is we're taking infinitely thin rectangles of this height and this width, and we're going to sum up all those rectangles from A to B and find out the area under the curve, okay, from some point A to some point B. And that is going to represent that area. Okay? And if we have thin rectangles, it fits it perfectly. So this is what we're kind of getting at. We want to connect this area to this sum or this integral. And what is happening here is that when we look at the velocity time problem, okay, so this is our velocity. The area underneath the velocity graph is the displacement. Well, if we recall, the derivative of displacement, so change in distance over the change in time, is velocity. Well, the distance function is the antiderivative, essentially, of velocity. We undifferentiate to get the displacement. So these things seem to be related. And in fact, they are related. They are very closely related.